probability mass function or PMF, which is also called as probability density function. It is PDF. So it is the function that represents the density of probability for continuous random variable over the specified range. Uniform distribution is a distribution whose probability for equal likely event lies between a specified range. Hello everyone, I welcome you all to the second session of Unit 3, that's under Statistical Computing and R Programming. So over here the Unit 3 is none other than Statistics and Probability. So I'd request we have one more session before this. So with respect to this unit, please go check that video too. Over here, my name is Deepa Kutnikar. I am working as an Assistant Professor under Department of Computer Science, Vidhyaashram, Temple of Excellence, MYSURU. So now let's see what is the thing that we have discussed in our session 1. So we did discuss regarding these things like what is statistics, what are the key aspects of statistics, then followed by probability, what is probability and what are the different types and the rules of probability, then followed by what is mean by data visualization, and we did also discuss the different types of data visualization techniques. So these are the things what we have discussed in our session 1 of Unit 3. So now let's see what is the agenda of today's session and what do we discuss in our today's session. So this is all about the agenda of today's session, where we'll be discussing what is probability density function, what are the different probability distributions, and yes, under that type we have multiple subtypes like Bernoulli, binomial distribution, Poisson's distribution. So these are the distributions under the discrete probability distribution. Then we also have continuous probability distribution. Under that we will be learning what is uniform distribution, Gaussian distribution and students t distribution. So these are the things that we discuss in our today's session, and let me tell you, this is one of very important session with respect to your Unit 3, because these are few important things that you can expect for your exams. So this is all about the today's session. So let's move forward and understand what is this probability distribution is. This probability distribution is a function that assigns probability to each possible outcome of a random variable. There might be some variables which misses probability, but by using this probability distribution we will be distributing probability for each and every variable. That's nothing but probability distribution. Alright, now let's see what does it describe. It describes the likelihood of different values that ranges, and we can say it is been represented or assigned to different random variables. So now let's see what are the different types of probability distribution. The first type is none other than discrete distribution. So discrete distribution, it describes the probability of distinct as well as countable outcomes. So we can say example, that's our dice example. So that is a discrete distribution. Then followed by continuous distribution. So this is a second type of probability distribution, where we can say it describes the probability of outcomes that can take any value. Please note that can take any values with a specified range. There will be some range, and within that range the probability will be mentioned or specified. So these are the different two types, the discrete distribution as well as a continuous distribution. Now let's move forward and see what are the different characteristics of our probability distribution. So yes, the first character is probability mass function or PMF, which is also called as probability density function. It is PDF. So now what does it describes? It describes the probability of each outcome. Then followed by cumulative distribution. So this cumulative distribution describes the probability of outcomes that is less than or equal to a specified value. So please note, over here under cumulative we only represent the values that are less than or equal to the specified values. Then the next one is a mean. So we have mean studied in our basic maths, right? So yes, even here we will be specifying mean with each and every distribution. So mean, it represents the expected value of some random variables. So we can define like this might be the expected outcome. So that's where the mean and the variance. So variance is a measure of the spread or dispersion of the random variable. So all these are the different properties that we study with each and every distribution. Like we have multiple subtypes under discrete distribution, even under continuous distribution. So these are the properties or the characteristics which we will define or we can define with each and every outcome. So why is it? Because defining this makes the distribution more precise as well as more organized. So that's why we will be going with the probability distributions. So let's move forward, and over here the function, the probability mass function, how is it defined? So it defines the probabilities of the discrete outcomes. So it has an expression. So let's see that. The formula for that is we are assigning some value, that's x, which is f of x. So how to represent that? It is represented in the form of sigma f of x equals 1. Okay. So now what are the different examples that we can consider under this probability mass function is Bernoulli's distribution, binomial distribution, as well as the Poisson's distributions. Alright. So now let's see one by one like what are these distributions are. So over here, starting with our Bernoulli distribution. So we can say this is a special case of binomial distribution, okay, where only a single trial is performed. Also we can say the discrete probability distribution for a Bernoulli trial has one trial and it will be provided with two outcomes. So either it might be a success or it might be a failure. It doesn't matter, but you are provided with the two outcomes. So that's all about Bernoulli distribution. As we deal with the two outcomes, it is called as binomial distribution too. Okay, so this is nothing but Bernoulli distribution. Now let's see what is the expression through which we can define this P of x followed or defining x. Then what is the value? So over here we can see p power x followed by 1 minus p to the power of 1 minus x, comma x, it varies from 0 to 1, where we can see x belongs to 0, 1. So this is a range. So let's see how to represent it this in a form of our keyword. So we are using d binom, okay. So this is a keyword in order to represent our Bernoulli distribution. So why d binom? As we know, Bernoulli distribution is a part of binomial distribution, right? So we are using d binom followed by what is the size. We have to define the size as well as the probability. So we have defined size as 1 and the probability has 0.5. So over here we can see p of x, the probability of x has been defined with 1, where we get the probability of 0.5 for that we have directly considered inside this statement. So this is all about Bernoulli distribution. Now let's move forward and understand like what exactly is binomial distribution. So let's start here. Binomial distribution is a type of discrete distribution. Alright. So what is it? It has only two outcomes. So even here the outcome will be either a success or a failure. Now what we can say, all its trials are independent and we can say that the probability of success remains the same and the previous outcome does not affect the next outcome. So this is the main point to note, where we can say the outcome is complete independent. It is not at all dependent on your previous outcome. So now let's see the expression for that. So this is the expression p of x we are defining to k. It gives n by k, p of k followed by 1 minus p to the power of n minus k. So now let's see an example. What is that? The number of heads in 10 coin toss. So for that we can write a example by using our programming keyword. We are again using the binom because we know we are dealing with binomial distribution, right? So now let's see the size, that is 10. Why? Because I am going with 10 coin tosses, right? Next probability is 0.5. How is it 0.5? As my number of trials is 3, I can define the probability as 0.5. Now you can also ask, what is this D over here in a keyword? It represents, it forms in a discrete distribution, alright. So this is all about binomial distribution. Now the next type of distribution is a Poisson's distribution. Let's see what is Poisson's distribution is. Absolutely, even it is a form of probability distribution, and here it describes the number of events that occurs within a fixed interval of time or space. Please note this over here, Poisson's, if we consider Poisson's, here it is the outcome will be representing based on the fixed interval of time or of space, alright. So let's define this. So how to define this? By using this expression. So let's see what is this. If lambda is a mean occurrence per interval, then the probability of having x occurrences can be provided or defined as p of x equals k equals e power minus lambda into lambda k followed by k factorial. So let's see what are these terms in our upcoming slides. So over here we can say P of x is been defined by k, which represents probability of observing k as an event, and we can also say E, we can say it has a natural log, okay. Now let's see what is this lambda. So lambda is nothing but an average rate of event occurrence, alright, followed by k is the actual number of events that is being observed, then followed by k factorial. This denotes the factorial of k. So this is all about the terms. Then we have considered an example like the number of phone calls in an hour. So for that we are defining with a keyword for our programming, that is D, Poise. So D, it represents the discrete distribution, right? And as we are dealing with Poisson's distribution, we are writing POIS, okay. So this is a keyword, and inside that we are defining our k term, lambda term and all, okay. So yes, I have defined a x, then I have defined a lambda. So this is being considered like I am defining the probability, or I am defining the x, that's a k value 4 and followed by a lambda value 2. So this is how we can represent in our R programming format. So this is all about our discrete distribution. Now let's move forward and understand like what is probability density function, which is also called as PDF. So yeah, let's see the definition first. So it is the function that represents the density of probability for continuous random variable over the specified range. So please note this, it is been defined only with respect to continuous random variables. Now let's see like what is the importance of this PDF function is. So PDF tells us like what is the relative likelihood of a range, and then what is the distribution shape. Also it can represent the expected value as well as the variance. So if you get these things, it will be very helpful to make a decision, right? So for that we can say this PDF is one of a best term or the property that we can utilize in order to represent the continuous values, or we can also say the continuous random variables. So this is all about PDF function, which is nothing but probability density function. Let's move forward and see properties with respect to this. So over here for continuous random variables, we can define a function which is defined as f of x such that it will be ranging from a to b followed by integral of a to b f of x dx, okay. Now the first property under that is f of x, if it is greater than or equal to 0, for all x, okay, it holds good for all x. Then followed by the second property, integral of minus infinity to plus infinity f of x dx will be 1, okay. So these are the basic properties with respect to the PDF function. Let's see what are the different continuous distribution that we have. So starting with the first one, uniform distribution. So uniform distribution is a distribution whose probability for equal likely event lies between a specified range. So as we know, it is a continuous. Over here the probability lies between the specified continuous part of region. Alright. So it is also called as rectangular distribution too, which is also called as rectangular distribution. Please note that it is none other than uniform distribution. Followed by, let's see an expression for our uniform distribution. So we are defining it as 1 divided by b minus a, where the x ranges from a to b. Alright. Let's consider an example over here, the random number between 0 and 1. So for that, our syntax is we are assigning a x value with our uniform. Yeah. So 1000, I am defining the continuous value, right. So I have to define a minimum value as well as a maximum value. So minimum value, it starts with a 0 and maximum it goes until 1. Alright. Now as I know, this is a uniform distribution and it forms in a rectangular format. I am representing a hist or histogram data representation, okay. So inside that I am representing the x value, then followed by the title, which will be a main distribution, then followed by the color through which I want to represent my data, then followed by the x label. So this is a basic syntax. So now let's move forward and understand the next type of continuous distribution, that's a normal distribution or a Gaussian distribution. Please note, normal distribution is also called as Gaussian distribution. Even this is a type of continuous distribution. Alright. So now let's see what it is called. It is a type of distribution that is symmetrical about its mean, also called as Gaussian distribution. Now let's move forward and know like how is it denoted. So yes, it is denoted as n of x bar followed by sigma square, where x bar is nothing but a mean and sigma is nothing but a variance. So the graph of the normal distribution is bell-like graph. So the bell-like graph is nothing but a normal distribution representation. Let's see what are the parameters. So as I already told, we'll be having multiple parameters like mean, variance and the cumulative distributive functions and all. So over here for the normal distribution, the mean what we can define as a mu, okay. Now standard deviation is a sigma. Standard deviation has been represented by a sigma. Then the PDF, that's the probability density function expression for our normal distribution, can be represented as f of x minus 1 by sigma root of 2 pi into the logarithmic base e, or we can also call it as natural logarithm, the power of minus x minus mu square whole divided by 2 sigma square. So this is a expression. So now what is the application of this normal distribution? So yes, it is used in Heights IQ test, okay. Now let's see a small example with respect to our programming. So I am defining a x, or we are assigning x with a sequence of values, that is from -4 to 4 with a length of 100. Alright. So now let's see what we are using, the keyword, that is a denorm, okay. So now we are defining mean and the standard deviation. Alright. Next we have to represent a plot, correct, because I want to represent my data in a good visualized form or in a good pictorial form, right. So for that I am defining plot of x comma y. Over here what I am defining is type equals L. L is nothing but line chart. Do you remember? So yes, also we are defining the main heading which is called as standard normal distribution, then followed by a color. So, this is how we can represent the thing or our plot by defining in our format. Next is a student's t distribution. Over here, let me say even this is a form of continuous distribution. Now, let us see what is this student's t distribution is all about. So, we can say this is used when either of this criteria is followed. So, when our sample size is less, okay, that is my first criteria, or I can also go with students t distribution when the population varies, that sigma square, okay. Also I can say whenever the variance is unknown, at that time I can approximate the normal distribution as sample size grows. So, these are the three different criteria when we can go with the student's t distribution. So, you can observe even here we can say the sample size will be small and it will be continuous, alright. So, let us see the application where this student's t distribution is used. It is used in a hypothesis testing, okay, and even in the intervals, which confidence, in the confidence intervals, alright. So, this is a basic typical application of our student t distribution. Now, let us see a small example over here with respect to our syntax. So, we are defining or we are assigning a set of sequence from -4, 4 with a probability of 0.1, okay. Now, again I am defining some set of value for y, that is a x and data frame of 5, alright. Now, let us see a final plot. So, what is that plot? Plot of x comma y comma the type. So, the type over here that we have defined is a L. So, what does the L represent? It is none other than the line chart. So, for that, so the main heading will be this t distribution followed by the color of the line. So, this is how we can represent the student's t distribution by using the R syntax. So, this is all about student's t distribution. Yeah. Thank you.